Hey everyone, welcome to Unit 2. I hope that your Unit 1 mini assessment went well, and that you're getting the hang of how you're going to be assessed for the remaining 8 units, and of course that your Unit 2 assessment goes just as well, if not better. Now the slide that we start on for this unit is a slide you've already seen. You saw it in Unit 1A, and it was just meant to remind you that we can do analysis not just on one variable, but on two variables. And we're going to start looking, because that's what Unit 2 is about, it's the relationship between two variables. We're going to start by analyzing the relationship between two categorical variables from a two-way table. Now there are three relative frequencies that we really care about in this unit. You need to be comfortable calculating them, interpreting them. Honestly, you need to be comfortable not confusing them, because that tends to be the hardest part for people. The first is the marginal relative frequency, and I'll just give you the hint. It's called the marginal relative frequency because the entire calculation happens in the margin. This is a subtotal over the grand total, and again, it represents the percent or the proportion of individuals in the data table that share one specific value for one of the variables. So out of the three relative frequencies, this is the only one that only looks at one of the two variables. Next, we have a joint relative frequency. So in this case, we care about both variables and we care about them at the exact same time. So what we're saying is it's the percentage or proportion of individuals that share one value for one of the variables and one value for the other variable. So for example, 445 of the individuals surveyed were not members of an environmental club and never used a snowmobile. So you're going to take that joint frequency, 445, and you're going to divide it by the grand total, 1526, for a joint relative frequency of about 29.2% or 0.292 expressed as a proportion. And last but certainly not least, we can look at a conditional relative frequency where you're looking at both of the variables, but one at a time. And so the idea here is you're going to take a joint frequency and divide by a subtotal. So in this example, we can look just at the people who are members of an environmental club and ask ourselves the question, what percentage or proportion of them own snowmobiles? Again, so we're going to take the number of people that both own snowmobiles and are members of an environmental club and divide that joint frequency by just the subtotal, the number of people that are members of an environmental club. Now, if you did that for all of the values for snowmobile use type, that would be the conditional distribution, okay, of snowmobile use for environmental club members. Again, a distribution, just like in Unit 1, is what are the values that are possible and how many of each. So in this case, we're looking at it as a relative frequency, not a frequency itself, but we're saying 69.5% of an environmental club members have never used a snowmobile, whereas 25.2% of them have rented and 5.2% of them own snowmobiles. That's the conditional distribution. So just as a reminder, we've learned three graphs that are appropriate to show the relationship between two categorical variables. We've learned the side-by-side bar graph, the stacked or the segmented bar graph, and then the mosaic plot in that order. And either from the stacked or segmented bar graph or the mosaic plot, it's very easy to see if there's an association or that there isn't an association between two categorical variables. And the way that you do it, okay, is you look at the height of the bars. The corresponding bars, if they all have the same heights, then there's no association. Again, an association is whether knowing the value of one variable would help us predict the value of the other. So if the same percentage of environmental club members versus non-environmental club members have owned snowmobiles, then knowing whether somebody's an environmental club member would not help me predict whether they own a snowmobile or not, right? Because they're completely independent. But if those conditional relative frequencies differ, or if the height of those bars differ, like in the case of the higher of the two graphs on your screen, then it would absolutely help us, right? It looks from the picture that you are much more likely to have never used a snowmobile if you are a member of an environmental club than if you are not. So just remember, association does not necessarily imply causation. We'll talk much more about this in Unit 3, but it's your first reminder from Unit 2. Now, The meat of the unit, Unit 2, is much more about two variables of quantitative data. We call that bivariate quantitative data. And again, just like with categorical data, you're going to measure two variables from the exact same individuals. And in this case, they need to both be quantitative, and we're going to represent them with two columns of a data table like you see on the screen, and eventually summarize them graphically with what we call a scatter plot. So you've got to pick one of the two variables to be the explanatory and to be the response variable. Again, these are your dependent and independent variables from elementary and middle school. But of course, the response variable measures the outcome of a study, and an explanatory variable is what you're going to use to try to help predict or explain changes in the response variable. Now, just like I said a minute ago, you've got the scatter plot, which is the view that you're going to use to show the relationship or the association between two quantitative variables. And the explanatory variable is going to go on the x-axis, so it's easy to remember, explanatory x-axis. The other variable, the response variable, goes on the y-axis. In this case, we're trying to predict ice cream sales from temperature at noon. And we can clearly see that there's a relationship. We're going to talk in a minute about how to actually describe that relationship. And just make sure you're not using the word cause, because again, we learned a minute ago, correlation does not necessarily imply causation. So we can't say that higher temperatures cause more ice cream sales, just that a relationship exists. And again, we're going to talk about how to describe it appropriately in a second. So the key to describing a relationship between two quantitative variables from a scatter plot is very, very similar to what we did in Unit 1 with SOX. You're going to look for the overall pattern and mention any departures from that pattern. But this time, instead of the acronym SOX plus context, we're going to use the acronym DUFS plus context, where DUF stands for direction, form, strength, and unusual features. And again, don't forget your context. It's really, really important. So direction. There's three directions that you're expected to know how to distinguish. We've got positive, we've got negative, and no association. And again, very easy to remember, positive association is when, as you increase the explanatory variable, the response variable values tend to increase as well. Negative is as you increase the explanatory variable, the response variable tends to decrease. And no association is if moving to the right or to the left on the x-axis doesn't really help you figure out where to go. It looks like this bottom picture on your slide now. For form, there's a lot of different ones, but on the AP exam, it's safe to always go with linear or non-linear. So on your screen here, we would say the first is linear, the second and third are non-linear, and just like always, we can say no association, and that's what that last one represents. We've got strength. So strength goes all the way from strong, okay, to moderate, to weak, and to no association. And when we're thinking about strength, we're thinking about how well do the points fit together to form a very clearly recognizable pattern, okay? Of course, the last one is unusual features. There's two major types that we learned, clusters and outliers. So you can see some scatter plots have both clusters and outliers, some just have one or the other. So again, just a quick summary. In order to describe a scatter plot, make sure you address all 4 points. This is very, very common FRQ topic for Unit 2, direction, form, strength, and unusual features, and do so in context, meaning use words from the problem to make sure that the reader understands that you know what the relationship actually is between two real-world variables. Now, Unit 2 FRQs tend to be multiple parts, but Part A for most of them is to describe the association between two quantitative variables. They give you a scatter plot like the one that you see on the screen, and you'd be expected to produce an answer like the one that you see as well. So if this is not something that you feel ready for, I'd recommend pausing the video at this point, reading the answer, and making sure that every part of it, every component of DUFs plus context makes sense to you. Now, a topic that's related to scatter plots and super commonly tested on the AP exam is the concept of correlation. We have the correlation coefficient R, which measures the strength and the direction of specifically linear relationships. So it's inappropriate to use correlation to describe a relationship that's not linear, and you have to remember it measures both strength and direction. At this point, you should remember that positive correlations have a positive slope if you were able to fit a line through a linear relationship. Negative correlations have a negative slope, describe negative relationships. So it should be very clear to you at this point in the course which of the scatter plots on the screen are positive associations versus negative associations. But just remember, the stronger the association, the higher the absolute value of the correlation coefficient R. So again, feel free to pause the video, make sure that you can understand why the highest correlation coefficient is the 0.91. Again, it's positive, and the points form a pretty clear linear relationship. Even stronger, but in the negative direction, is the one directly to the right of that one. And the first one I want to draw your attention to is the correlation R equals 0. Again, there is no association here. We can't tell whether it would be positive or negative. It doesn't look like a line at all. That's why it's going to be very, very close, if not exactly equal to 0. Now, College Board loves to assess whether you truly understand correlation, and they do so through some very, very common properties. So it's always a number between -1 and 1. Again, the direction of the relationship, of the linear relationship, is indicated by the sign. So positive values of R for positive association, negative values of R for negative association. A -1 or a +1 only occur in the extreme cases of a perfect linear relationship that's either negative or positive respectively. If it's strong, it's going to be very close to -1 or +1. If it's weak, it's going to be very close to 0. Now imagine you're asked to discuss the strength of a linear relationship. One way to do so would be to look at the value of R, which you can either just be given directly or given something related to it like R squared or the individual points, and you can actually solve for R. But the idea is, how do you translate a value of R to the strength of a relationship? And so we've got some pretty common rules of thumb that you can follow. So values that are very close to 0, you're going to say no relationship, no association. Values that are between 0 and 0.5 on either side of the number line are considered weak. Between 0.5 and 0.8 on either side of the number line are considered moderate. And between 0.8 and 1 on either side of the number line are considered strong. So by now, most of us have forgotten the formula for calculating R, and the great news is you'll never have to do that. Your calculator can do it for you, or it'll be given to you. But it's really just important to understand what the formula represents. So you have it on the formula sheet, but I'll walk you through it. It's essentially the average, and I say essentially because you're dividing by the number of points minus 1 instead of what the true average would be, dividing by the number of points. But you're taking the z-score for each of the points in the horizontal and the vertical direction and multiplying those z-scores. You're adding them up and dividing by n minus 1. That's why, by the way, because you're taking the sum of the product of the z-scores, that's why points that lie far from the mean in either direction, x or y, have so much overwhelming influence on the correlation coefficient relative to points that are close to the mean, close to where the other points are. So you can pause the screen here if you want to think about that, but that is a very special property of the correlation coefficient formula. And just a couple key reminders that you could actually work out directly from the formula, but there's no need to if you can keep these things in mind for the AP exam. Both variables, of course, have to be quantitative. There is no distinction in terms of the correlation coefficient between the explanatory and the response variable. So if a question asks you what would happen if you swapped the x and the y variable, it would make no impact to the correlation coefficient. Of course, if you look at the formula, that should make perfect sense. You're just adding the product of the two, and 2 times 5 is the same as 5 times 2. If you change units of measure of one or both of the variables, the correlation coefficient does not change because, again, you're standardizing when you convert to z-score in both directions. And the correlation coefficient has no units of measure. It's just a number between -1 and 1. And I'm just going to touch on 2 of these cautions, but just be careful. Correlation coefficient does not measure form, so just because it's a close to -1 or +1 R value doesn't mean the relationship is linear. You should actually look at the scatter plot for the form. And it is not resistant. Of course it's not resistant because it takes into account every single point, so one outlier in regression can completely throw you off. So why is any of this useful? And of course, this is the setup for what we need to make future predictions. And again, this is, in my opinion, among the cooler topics that we learn in the class, because you get to learn how to predict things that haven't occurred yet. Now, this is the exact same slide you saw a few minutes ago. The difference is we've added a line of best fit to the scatter plot on the right. That is eventually what we're going to define as our LSRL, or our least squares regression line. A regression line, which is just a line of best fit, represents the predicted change in the response variable for changes in the explanatory variable. And we have a common form that we use for the regression equation. I'll show it to you on the next slide, but you can already see it here. So y hat equals a plus bx. We'll go through the variables first and then the constants. So x is a given value for the explanatory variable. Y hat, and the hat's very important, don't leave off the hat, is the predicted response variable for the value of x that you've already plugged in. A and b, like I said, are constants, where a is the y-intercept of the model, so it's the value when x equals 0, and b is the slope of the model. And we'll talk about how to interpret these in a minute. But just be careful, we don't write y hat equals bx plus a, we write a plus bx on the AP exam. It's very important that you stick to that version of this equation. Now just remember, this is a review video. This is not absolutely every detail from the original slides. So if you want to do any of the problems that come up, you're welcome to pause the video to do so. But on this slide, we were talking about making predictions. And the idea is, if you were given an appropriate value for the explanatory variable and you want to find out what the predicted value of the response variable would be, and you have the regression equation, all you have to do is plug in that value for x. And here you can see we're plugging in 100,000 miles to get a predicted price of $21,967 for a Ford F-150 that's been driven 100,000 miles. Now, if we were asked to do the exact same exercise, predict the price of a Ford F-150 that's been driven 300,000 miles, you could not follow the same steps. And the reason why is because this would be considered an extrapolation. The use of a regression line for prediction far outside the intervals of x values used to obtain the line. So these are not typically accurate predictions, and you should be very careful. You as the student or the statistician in the real world are responsible for knowing when it's appropriate to use a regression model and when it's not. One of the more complex topics that we got to in Unit 2 was residuals, and I know it's been a long time, so feel free to pause the video or look for refreshing material on this topic specifically. But the idea for a residual is this is the leftover variation, the variation that cannot be explained by the relationship between x and y. Again, we're going to try to explain as much of it as we can, but if the line were to pass perfectly through all the points, then you wouldn't be making any money in the real world for predicting this thing. It's something that clearly is very easy to predict. The reason why regression is useful is because we can predict things that are variable or have unexplained variability. So the residual is the vertical distance between your prediction and the actual value for data points. Of course, we want these residuals to be as small as possible. And mathematically, they are the actual y value, or the actual value of the response variable, minus the predicted value of the response variable. And I taught you guys my little acronym, AMP, for actual minus predicted. So in this case, it's asking us to calculate and interpret the residual for the truck that was driven 70,583 miles. And again, we just want to do actual minus predicted. So to do actual, we just look in the table. We can see that the actual price was $21,994. But what would be the predicted value? And of course, this is not extrapolation, so we can just plug that mileage into our regression equation. We get a predicted price of $26,759. And so we're going to do 21,994 minus 26,759 for a residual of negative $4,765. So in this case, the actual price is less than the predicted price. That's why the residual is negative. That means that the model over-predicted. The model over-predicted when the residual is negative, right? That means that the point is under the regression line. So, of course, we want to use residuals not just for the sake of understanding how far off our predictions were, but for understanding how appropriate a linear model is in the first place. The residual plot is a super useful tool for that purpose. And so, again, we've already set up your calculators to be able to graph scatter plots as well as residual plots. If you've lost that setup, you can come to me at any point and I will help you set it up. Of course, not during the mini assessment, but outside of that. But the idea is a residual plot shows the residuals on the y-axis. On the x-axis, you have your explanatory variables, and you're hoping to see no pattern. You're hoping to see random scatter in the residual plot, like you see here on the right. So again, that's the goal. If you do see leftover curves or patterns in the residual plot, it likely means that a linear model was not appropriate for the data set that you used to make the residual plot. What the residual plot actually does is it magnifies the deviations of the points from the line. So one of these two is an appropriate, so both of them are residual plots, but one of them is a residual plot that represents an appropriate linear relationship, and the other is one that does not. And of course, it's the one on the left, which represents an appropriate linear relationship between two variables, and the one on the right that definitely doesn't. There's a very clear parabolic shape, meaning there was a curved pattern in the original scatter plot. And just to be clear, there is an advanced version of a question on the AP exam that they tend to ask every couple of years, where they ask you to use a residual plot for a different purpose, which is to reverse engineer the actual value of the response variable for a given value of the explanatory variable. And you're welcome to pause the video here and see if you could do that. So again, just a couple cautions to highlight here. Make sure before you use linear regression that you look at the scatter plot, that you make sure the relationship looks linear, that you look at the residual plot and make sure that there's no curve or pattern. Please make sure you do not go backwards. You cannot just rearrange the formula to solve for x. You cannot predict x from y, only y from x, and don't extrapolate. Now, there's a lot of interpretation questions that come from this part of the unit, specifically on FRQs. Again, very typical that an FRQ starts with asking you to explain or describe the association or relationship between two quantitative variables from a scatter plot, but then very quickly they ask one or two interpretation questions, and there's at least 4 things that they could ask you to interpret. Typically, they'll ask 1 or 2. So in this case, A, the y-intercept, is the predicted value of the response variable when the explanatory variable equals 0. And again, it's important to do this in context to give units of measure for both variables if you have them available. B is the slope. So this is the amount by which the predicted value of the response variable changes when x, your explanatory variable, is increased by 1 unit. And again, you want to give units of measure here too. Now you're more than welcome to pause the video here to see how this is done in context for the problem of the Ford F-150. But what I really wanted to highlight on this slide was the fact that it's really, really important that you use the word predicted or expected or on average, something that shows the reader that you understand that the increase in y for every 1 unit increase in x is the expectation or what you're predicting to happen, not necessarily what will actually happen in practice. Now, our line of best fit in AP statistics is what we call the LSRL, the least squares regression line, and it's the line specifically that makes the sum of the squared residuals as small as possible. And it's got a couple important properties, the first of which is the fact that it always passes through the centroid, which is the point x bar comma y bar. So it passes through the mean of the explanatory variable from the sample and the mean of the response variable from the sample. Now, of course, the least squares regression line is the best you're going to do, but the question is, how reliable would predictions be based on that least squares regression line? And of course, this depends on the variability of the response variable that can be attributed to the relationship between the explanatory and the response variable. We've got 2 measures that we're going to use to measure reliability. The first is S, the standard deviation of the residuals, which is the typical size of the residuals. We also have our squared or our coefficient of determination, which quite literally is your correlation coefficient R squared. Okay, so it's always going to be non-negative. It's impossible to have an R squared value that is less than 0, but it measures the percent reduction in the sum of the squared residuals when we use the LSRL to make predictions rather than just predicting Y bar for all values of X. And again, we say it measures the percent of the variability in the response variable that can be accounted for by the relationship between the explanatory and the response variable. We want R squared, of course, to be very high. So you can pause the screen here for the interpretation of both in context for the Ford F-150 problem. This is something that you would be expected to do on an AP FRQ. You can see all 4 values that you could be expected to interpret: A, the y-intercept; B, the slope; S, the typical residual size, or the typical prediction error is another way to think of S, and R squared, the coefficient of determination, from computer statistics software output. Minitab is the most common, but there's a couple others. You should practice just becoming familiar where to find each of the values, because we're asked to interpret it. Part of interpreting it on the AP exam is identifying the correct value that goes along with your interpretation. So there's a couple different ways to find the equation of a least squares regression line. The first of which is the least common and algebraically the hardest. But essentially, you would use the formulas on the formula sheet that are reproduced for you here to find B first by taking R and multiplying it by the standard deviation in the y direction over the standard deviation in the x direction. And then you're going to plug that in to the formula that is here on the right: y bar equals a plus bx bar. You're rearranging that formula to solve for a. You're plugging in your y bar, your x bar, and your b, and you're going to get a, the y-intercept. Of course, much easier than the method we talked about on the prior slide would be if you have the individual data points, you can just plug them into L1 and L2 in your calculator and ask the calculator to give you the least squares regression line, which it can absolutely do. Make sure you review both methods, find sample problems for each, and make sure that you're completely comfortable. The easiest method is just to be given the computer output and to find A and B and put together the equation of the least squares regression line. We've got points on linear regression models or in scatter plots that are special. 3 types that we want you to be familiar with: so high leverage, outliers, and influential points. So high leverage points have much larger x values, larger or smaller if they're on the left side of the scatter plot, than other points. Outliers don't follow the general trend of the other points in the scatter plot, and influential points are points that, if you remove them, would substantially change one of the features of the least squares regression line. So an important property that we already talked about as it relates to the correlation coefficient R, but it now also applies to the LSRL, is that these are not resistant concepts. So one outlier can really influence the least squares regression line. So here are some points, and the least squares regression line is this one in blue. But as you can see, you really just have this one extreme point pulling up the regression line. If you were to remove it, look at how different the least squares regression line would be. And again, that is an extremely influential point. So just to review a couple, and you're welcome to pause the video and review these in more depth. The point that's circled in red here is both an outlier in the x direction and in the y direction, so it's got a much larger value in the x direction, a much smaller y value than the other points. But this is considered a good point. It's not considered an outlier in terms of regression because it does follow the general trend. But what this is going to do is it's going to extend the pattern. So it doesn't change the slope by much. It increases our correlation coefficient R. This value that's circled here is an outlier only in the y direction, so it does not follow a general trend, so we call it an outlier in terms of regression. It doesn't affect the slope too much, okay, because it doesn't have a lot of leverage, which we'll talk about in a second, but removing it would increase the correlation coefficient R because it would be a better fit to the pattern and could slightly change the y-intercept. So if you remove it, the y-intercept would slightly go down. Finally, you've got an outlier in the x direction only, so we call these high leverage points. They can significantly change the slope, and they are considered influential. So if you remove them versus add them, the slope will completely change to accommodate them, because otherwise they'd have a huge residual. This is the website that we use, and I will happily send this link to anyone who wants it, where you can actually use points that you can rearrange as you see fit in order to explore how the least squares regression line responds to those changes. And you'll see that it always, no matter what you do, passes through the centroid. So the last topic in the unit is very important for anybody who wants to get above a 3, so a 4 or 5 on the AP exam. And it's a reminder that regression and correlation only describe linear relationships. So it's not enough to just look at the correlation coefficient R and say it's pretty high. As you can see, all 4 of these scatter plots have the same correlation coefficient R, and only one of them should be modeled with a linear relationship, and that would be the top left one. The bottom left one could, but you have an outlier there that you should probably remove, and then you'd get a great fit. So if you're ever given a scatter plot or data to make a scatter plot where the relationship between the explanatory and the response variable looks pretty strong, but the relationship doesn't look super linear, maybe there's a curve, maybe it looks exponential, what you want to try is to apply some common transformations to that data and see if you can get the transformed data to look like a linear relationship between x and y. The raw data on the prior slide is a perfect example of this, where if you plot it, it's not going to look, the scatter plot's not going to look linear. Now you want to make sure, so you plot the residual plot and it's going to look just like this. There's a very clear U shape. That's a very clear evidence of a curve in the original relationship. So we know that even though there seems to be a relationship, it doesn't seem to be linear. So we want to apply a transformation. One common transformation is to take the log of both variables, and there are a couple other popular ones, but in this case, we've taken the natural log. We look at the scatter plot of ln of x versus ln of x, and the relationship actually looks fairly linear, so we want to make sure we check the scatter plot, and you can see here it looks like random scatter, which could imply that the underlying transformed data has a linear relationship. So we now write the linear regression equation. So instead of y hat equals a plus bx, we write the transformations that we did to get this data. So we write ln of y hat equals a plus b times ln of x. And we just plug in the values. And what you have to do is you have to undo the transformation. So we're going to be able to solve for ln of the predicted weight, but we want the predicted weight. We don't want the natural log of the predicted weight. So to undo natural log, we raise e to that power, and we get our predicted weight of 10.42 grams. And again, I challenge you to pause the video, see if you can do this problem on your own. Now, these are the common transformations that you can try. Some teachers recommend that you actually learn which transformation to try when, but it's quick enough with our TI-84s that we can try all of these fairly quickly. So it's up to you whether you want to learn which to apply when, or whether you just want to learn what are the 4 common transformations that you should try. But it's very uncommon that on the AP exam they'd give you relationships that aren't linear. So again, for people that want a 4 or 5, this is a tool to have in their back pocket. And again, this is the basic framework. So if the data does not look linear, you want to transform the data, look at the plot, look at the residual plot, make sure that there's random scatter. If so, you can undo the transformation and solve for your predicted y value. Otherwise, try another transformation and repeat the process all over again. But that's the unit. You should be very proud of yourselves, and you should feel confident for tomorrow's mini assessment on Unit 2. Again, if at this point you don't, additional resources are available. Khan Academy, AP Classroom. There's practice quizzes and tests in the Google Drive, which I would highly recommend for this unit, because we really haven't looked at Unit 2 in a long time. The good news is if you stayed up to date with Unit 9, then you reviewed a lot of these concepts already. But if you don't feel confident with Unit 9, definitely do some practice quizzes or practice tests, and make sure to check out some of the practice Unit 2 FRQs on StatsMedic. And have a great night, and I'll see you tomorrow.